Welcome to DV Earth Science. We're going to tackle Chapter 4 today, Earth's Structure and Motion. We have three sections: Earth's formation, Earth's rotation, and Earth's revolution. The first section, you can see the vocabulary list on your left, which is very helpful throughout the section. And there are four objectives. If you can explain how most scientists explain the formation of our solar system, if you can describe Earth's size and shape and the arrangement of its layers, if you can list three sources of Earth's internal heat, and if you could describe Earth's magnetic field, you have mastered this section. Now, the interior of the Earth is layered similar to an onion. It has peeled, like if you were to peel the onion off, it has different thicknesses, and some of them have different properties. Now, these layers are defined by their chemical, what they're made out of, or flowing properties, how they act when the temperature changes. Now, the four layers are the inner core, outer core, mantle, and crust. Earth formed about 4.6 billion years ago from a nebula, which is a cloud of gas and dust. It developed layers as it cooled and dense material sank to its center. It coalesced. Now, understanding of Earth's internal structure is based on observations of topography, that's surface land on the surface of the geosphere, bathymetry, that's the study of the bottom of the oceans, and rocks and outcrops. Now, seismology, the study of earthquakes, and volcanic samples provide evidence of Earth's interior. Now, the core is believed to largely be composed of iron. About 80% of the core is believed to be iron, and other lighter elements such as nickel. The inner core, solid iron, mostly iron, about 6,371 kilometers from the surface, and 6,000 degrees Kelvin. Now, the outer core is liquid. It's about 5,150 kilometers from the surface, and it is a little cooler than the inner core, and it does increase in temperature with depth. Now, the mantle is heated by radioactive decay of heavy elements. It is solid but has liquid properties. Now, it's about 28 or almost 2,900 kilometers from the surface, and its range in temperature is between 1,500 and 3,200 degrees Kelvin. Now, the crust is solid. It's between 0 and 65 kilometers from the surface. Its temperature is less than 1,000 degrees Kelvin. It does increase about 10 to 30 Kelvin per kilometer. Now, Earth's formation. There are several different theories out there, but one theory is the nebular hypothesis. That's the planetary nebula that Earth is formed out of. And this begins with a large cold cloud of interstellar dust and gas that begins to condense. Now, the cloud's material converges, they start colliding with each other, it gets faster, it grows hotter, there's more energy, and then a cool disk of ice and rock is surrounded by hotter gas. Then all of that starts to coalesce, and this fusion first occurs and a new star is formed. This is called, then around it, the planetesimals form. That's all the material out in that disk, and begin to attract more and more material as they orbit. Now, over time, nearly all the material from the original cloud becomes part of the star and its orbiting planets. Now, the crust and top of the mantle are further classified by their properties into the lithosphere and the asthenosphere. So you have the crust and the mantle can be broken up based on their properties. The lithosphere acts a certain way. That's the solid part that flows on the upper mantle. And then the asthenosphere has different properties, liquid-like properties within the mantle. So the inner core, here's a really good chart out of the textbook. Inner core, outer core, mantle, crust. It goes over the state at which it's in and the depth from the surface, as well as the temperature. Breaks it all down for you. Now, meteorite impacts, the weight of overlying material, and the decay of radioactive isotopes caused Earth to heat up very early on in its formation. Now, since then, it's been losing heat, it's been getting cooler, and those don't have as much of an impact on its temperature. Earth has a characteristic magnetic field that we will discuss. An electromagnet is a magnet that is created by the current that flows around a soft iron core. Now, Earth has a solid iron inner core surrounded by semi-liquid materials of the outer core that move in a continuous current around the inner core. Now, because of this movement, it actually is an electromagnet. Now, this is called the dynamo theory, and it produces something vital to life on Earth, and that is Earth's magnetic field. Moving on to 4.2, Earth's rotation. There are two objectives in this section. Give evidence of Earth's rotation and relate Earth's rotation to the day and night cycle in the time zones. There's a list of vocabulary terms that you should record in your lab notebook. Now, Earth makes one complete 360-degree turn on its axis about every 24 hours. It rotates at a rate of 15 degrees per hour. Its axis of rotation is tilted at 23.5 degrees with respect to Earth's orbital plane. Now, what an orbital plane is, as it orbits the sun, that orbital plane, as you can see that red line, they made it red because that's about equal, not perfectly, but about equal with the equator of the sun. So you can see we're tilted either towards or away from the sun, depending on the season and depending on the hemisphere. Now, if you're closer to the equator, that tilt doesn't have as much of an effect. You're closer to the orbital plane. Now, the effects and evidence of this rotation include the Coriolis effect, Foucault pendulum behavior, and day and night and sunrise and sunset. So here's another diagram looking at the different aspects and different characteristics of Earth's axis. Now, Earth rotates on its axis. We said it was tilted at 23.5 degrees. That right there is the reason why we have our seasons. Now, because Earth is a sphere, the distance around Earth decreases as the distance from the equator increases. So as a result, Earth's speed of rotation decreases away from the equator. So the fastest Earth rotates is at its equator. It's about 1,690 kilometers per hour at the equator, and at the North Pole it's 0. Boston, it's 1,300 kilometers per hour. Now, Earth is divided into 24 worldwide standard time zones that begin at the prime meridian. Each standard time zone is about 15 degrees wide. Here's a way to look at it if you were to set it up just like a clock. So midnight up at the top, noon at the bottom, 6 p.m., 6 a.m., and you can see where the time meridian is positioned as well. Now in 4.3, Earth's revolution. There are three objectives. Give evidence for Earth's revolution around the sun, describe Earth's path and rate of revolution, and explain why seasons occur. There's a vocabulary list on the left. Now, Earth revolves around the sun in an elliptical orbit with the sun as one focus. If you're not quite sure what an ellipse is, make sure that you see a picture or you find out a description of what an ellipse is. It's not a perfect circle. Now, evidence for Earth's revolution includes seasonal constellation changes. You don't see the same constellations every single season, and what's called a parallax, which we'll talk about here in a little bit. It's the apparent shift of a star's position. Now, Earth makes one revolution around the sun every 365.24 days. Now, parallax, one evidence of Earth's revolution, is when Earth revolves around the sun, nearby stars appear to shift position. This shift is called the parallax, and it's evidence of Earth's revolution. The diagram above shows two views of stars seen from Earth 6 months apart. Now, notice that the nearby star in the center seems to shift position relative to the very distant stars beyond it. So you see the very distant stars, but then you can see from position B, as seen, the larger star is on the left side of the circle, right here, and then from position A, it changes to the right. Therefore, our revolution is around the sun. Now, combined with Earth's tilt, revolution causes seasonal changes. The summer and winter solstices are the longest and shortest days of the year in the northern hemisphere, respectively. So the summer solstice up in Alaska is 24 hours. There's a day that there's 24 hours of daylight. And this is June 21st or 22nd, depending on the year. And the winter solstice is 24 hours of darkness, December 21st or 22nd, depending on the year. Now on the vernal, and the vernal is spring, and autumnal, which is the fall equinoxes, day and night are of equal lengths. So it's equal amount of sunlight, equal amount of darkness. To recap this chapter, we have Earth's formation And there's an outline. Origin of the solar system, Earth's size and shape, Earth's interior, Earth's heat, Earth's magnetic field. The second section was Earth's rotation, evidence for rotation, axis of rotation, effects of rotation, measuring time, standard time zones, the international dateline. And then Earth's revolution, evidence for revolution, path and rate of revolution, effect of revolution and tilt, the laws of thermodynamics, which we covered in the previous chapter, the effects of Earth's surface and human activity in the cycles. And that's it. Thank you.